This is a flip video about heating and cooling curves, an introduction. So this is an example of a heating curve. And what a heating curve is, if you notice, it's a graph, and on the bottom I have time. You can also have heat on the bottom, but it doesn't really matter, heat or time. And on this axis I have temperature in degrees Celsius. And what it does is it shows a substance as it's being heated. So this substance is water, as indicated in my title. And so water is going from all the different states of matter. So it starts off as an S for solid, then it turns from a solid to a liquid, then it goes to a liquid, and then from a liquid to a gas, and then a gas. And so if you note, there are some important things. For water specifically, you should know that water turns from a solid to a liquid at 0 degrees Celsius, and from a liquid to a gas at 100 degrees Celsius. Those are temperatures you should remember. So let's write that down. Okay. A liquid to a gas is its boiling point, 100 degrees Celsius. It's also called the point at which it evaporates. Now, in reverse, if we were to cool this, so instead of going from a liquid to a gas, we went from a gas to a liquid, cooled this down, it actually happens at the same temperature, 100 degrees Celsius. The only difference is I'm either putting in energy to boil or removing energy to cool. Same thing with the melting and the freezing point. Water going from a solid to a liquid is known as melting. That happens at 0 degrees Celsius. Water freezes going from a liquid to a solid at 0 degrees Celsius. They're the same process, it's just happening in reverse. To melt, you have to put in heat. To freeze, you have to remove heat. This process happens at these temperatures. Okay? All right. Then, going back to my graph, if you notice, there are some similar things on this graph. First of all, there's 5 segments. 1, 2, 3, 4, 5. So let's label that. We got here step 1, step 2, step 3, step 4, step 5, or 5 segments. Okay? If you notice, here's the same exact graph. I've got segments that are rising, seen here, written with blue, rising. So 1, 3, and 5 rise. And then I've got these horizontal segments, we can also call them plateaus, that are not rising, and they're just horizontal lines, so at 2 and 4. Okay? All right, we'll come back to that. So let's see what's happening. If you notice at 2 and 4, those are where my phase changes are happening, going from one phase to another. So I have 2 phases present here. They have the exact same appearance of a horizontal line. What's happening? Well, if you notice, my temperature is not changing at my phase changes. My temperature is not changing. It stays 100 degrees up here as a liquid goes to a gas, and it stays 0 as a solid goes to a liquid. Why? Well, because I'm pumping in energy, right? I'm pumping in heat to get this substance to go from a solid to a gas. So heat, which is energy, can only be doing one thing at a time. And so at all my phase changes, 2 and 4, energy, heat, is used to overcome the intermolecular forces and to loosen them up. Okay? And no temperature is changing, so heat can't be used to raise a temperature. Instead, heat is being used to, over here, loosen the intermolecular forces. Then over here, the intermolecular forces are going to be completely broken off so that it can turn into a gas. So in these instances, right, heat is being used to overcome, in other words, to break apart or loosen the intermolecular forces. Well, how about in the other segments? The rising segments, notice, are single phases. A solid, a liquid, a gas. I'm pumping in heat, and so heat is not being used to change anything. Instead, heat is raising the temperature. So heat, as you add it, is just speeding up, kinetic energy. It's just speeding up the water molecules. So the molecules are starting to gain more and more energy, more and more energy. It's not until here where they have enough to now loosen those intermolecular forces. Now it's in a liquid, their intermolecular forces are loosening even more, right? Or sorry, not loosening. Sorry. Now it's in a liquid, and the liquid is just being heated up, and the molecules are just moving around, moving around, moving around. Temperature is increasing. Then eventually now the heat is being used to break apart the intermolecular forces and not raise the temperature. Once all those forces have been broken apart, now the heat can be used to start raising the temperature of that gas. Okay? All right. Some other things that we should note and put on our graph is what we just said. That is, the phase changes happen at 4 and 2. Make sure you write that in. Those are where the phase changes happen. Remember, this whole thing, a solid going into a gas, these are just phase changes. And so phase changes are physical properties. I'm not changing water into a completely new substance. I'm just taking water from one state of matter and putting it into another state of matter. Okay, so another new concept that we're going to learn is a cooling curve. But it's really not new because it's the same thing as my heating, just in reverse. So notice I start off here up high at a high temperature with a gas, go from gas to liquid, liquid to solid, and then down to solid. Okay, so it's the same concept, it's just reverse. Heat is being removed instead of entering. Okay, all right, now, here are two new concepts that we should learn. Remember, this is change on enthalpy. We learned that in our previous chapter, change in enthalpy. Also known as kind of like a change in heat. So we call this a heat of, and VAP stands for vaporization, and then this one stands for FUS, which stands for heat of fusion. I'm going to start with vaporization first. You know vaporization is the same thing as evaporating, a liquid going to a gas. And fusion is melting or freezing. This one's kind of a new term for us. Melting or freezing is fusion. So if we bring back our 5-segment curve, we can label that here's where melting happens, and this is where I have my change of heat of fusion, F for fusion, and this is where I have my change of heat of vaporization. So we can label those parts of the graph as seen there. Okay? Now, every substance has its own heat of vaporization, so the heat needed to vaporize. And every substance has its own value of the heat needed to go from melting. These are water's values. You will be given these. You do not have to memorize them. The heat needed to, remember, fusion is melt or freeze. The heat needed to melt or freeze water is 334 joules per gram. The heat needed to vaporize or condense water is 2,260 joules per gram. If you notice, you need a lot more heat for vaporization. Why? You're breaking intermolecular forces. Here you're loosening them, here you're breaking them. Okay? Lastly, if I bring back this, we are going to learn in our next video how to actually do some calculations and calculate the energy. In other words, how much energy do I need for this solid right here to heat up? How much energy do I need from the solid to turn into a liquid? How much energy do I need for the liquid to heat up? How much energy is needed for the liquid to go to a gas? And how much energy is the gas need to heat up? So I'm going to calculate the energy at parts 1, 2, 3, 4, and 5. Okay. In order to do that, remember, here's my energy equation that we've learned already last chapter. Q equals MCAT. Q is energy, which is known as heat. M is mass in grams. C is specific heat capacity in joules over grams degrees Celsius. And triangle T is change in temperature. That's T final minus T initial. Please write those down, a refresher. So all of the rising segments, if you notice, they all have temperature changing. Temperature increasing, increasing, increasing. Temperature increasing, temperature increasing. So I'm going to use my Q equals MCAT. The reason why is because there's a change in temperature. Now, I can't use Q is equal to MCAT on the plateaus. Why? Because temperature is not increasing. Temperature is constant. So on the plateaus, I cannot use this equation. Okay? So what will I use? Look down here. My plateaus will use a modified version, and that is Q equals mass times the heat of fusion for this part, or Q is equal to mass times heat of vaporization for part 4. So I'll use this one for part 2 and this one for part 4. Okay? Remember, I've already given you the heat of fusion and vaporization. Some other things that you've learned in the past in videos are the specific heat capacity of water. I'm going to refresh your memory and hopefully you could write this down. This is specific heat capacity of water as a liquid. You know this one. But also remember we learned solid and a gas. You do not have to memorize these. It's just important to put them in your notes. That's the end of the video.